Earlier I mentioned how some of those have unused p orbitals, and I'm sure you're just dying to know what's happening. So let's talk about those unused p orbitals. And it has to do with multiple bonds. And we saw in the last chapter that sometimes these systems will make double and sometimes even triple bonds. So this is an example of CH2CH2, which is known as ethylene or formally as ethene. And we talked about how that's an sp2 hybridized system because it's a trigonal planar, stuff like that. But why is that top part flat? Like, why is the double bond just one cloud? Why isn't it a second cloud? And that's a great question.
The sigma bonds in ethylene come from the overlap of sp2 hybrid orbitals, one from each carbon atom.
Now, in the lower right-hand corner, that little video showed the sigma network, the single bonds in the molecule. So each of those little red dots is the nucleus of an atom. So on the outside, you've got the hydrogens, and on the inside, you have carbon. So carbon, if it's trigonal planar, will have sp2 orbitals, and there's 3 of them. So you can see that the red dots there in the middle, they have like 3 teardrops coming out. Each of those is an sp2 orbital. And then what we're looking at here really is the formation of the sigma network. So one of the sp2 orbitals on carbon connects with the atomic hydrogen orbital to make the sigma bond, the single bond that we see between carbon and hydrogen. But also we're seeing here how carbon and carbon can each have an sp2 orbital. They can have overlap, 2 sp2 orbitals to make a sigma bond as well. So in the molecule of CH2CH2 or ethylene, the first bond you see is a sigma bond. So I'm not talking about the double bond. I'm not talking about the top of the 2. I'm just talking about one of the lines. I'm going to use the bottom one here. But that's where the sigma bond comes from. The sp2 on the first carbon overlaps with the sp2 on a second carbon. That's where the sigma bond comes from. But where does the second bond come from? I haven't talked about that yet. Well, that last bond, the pi bond, which is what we called it in the last chapter, that pi bond comes from the unused p orbital. So carbon is 2s2, 2p2 when you're thinking about the atomic electrons. And if you have a trigonal planar carbon, like we have in ethylene, then we're going to have 3 sp2 orbitals. But notice how there's one unused orbital left, all right? And that's an unused 2p orbitals. And the 2p orbital on one carbon can combine with the 2p orbital on a second carbon to create a wild pi bond. And a pi bond is an area of electron density that's both above and below the sigma bond. And the closest analogy I can think of is that if you have like a sandwich, all right, the middle part of the sandwich, we'll say peanut butter and jelly, that would be the sigma bond. And then the pi bond would be the bread above and below your peanut butter and jelly sandwich, all right? And it's important to realize, even though you have maybe 2 slices of bread, that's one pi bond. It's both above and below the sigma bond. It's totally wild. This is an attempt, and not a very good attempt, probably as you can imagine, to show that unused 2p orbital. And you can see, which is the blue orbital, by the way, and you can see how it sticks out a little bit above and a little bit below the gold orbitals, which are the sp2 orbitals. And because it sticks out a little bit above and below, it can interact with another p2p orbital to make these pi bonds. It's totally wild. This is like science fiction as far as I'm concerned, even after all these years. It's so cool. But this is what the pi bond comes from.
The pi bonds arise from the overlap of unhybridized p orbitals, one on each carbon. Note that pi bonding electrons are found in a region above and below the sigma bonding region.
So remember how I called it the bread in the sandwich, above and below? That video right there represents one pi bond, and there's 2 regions of it, above the plane and below the plane of the molecule. So again, in the middle there, those are all the sigma bonds, and above and below that sigma network is where this pi bond exists. So we always said in the last chapter how trigonal planar, if you have a double bond like we have here, it was just just like one big cloud. And you can see why it is. It literally is one big cloud. It's not a separate cloud like in a tetrahedron. It literally is the same direction and all that kind of stuff, but it's bigger, but it is just one big cloud. So when you have a chemical with a double bond react, it's usually the pi bond which reacts first because it's on the outside. Not all the time, but a lot of the time. So you can see how this is just a wild kind of bonding, but it's pretty exciting.
When we look at both sigma and pi bonds, we see that the CH2 fragments are coplanar and that ethylene is a flat molecule.
So this shows the complete sandwich, if you will, the complete ethylene bonding that's happening when you have a molecule of it. And on the inside, you have the sigma bonds. Those are the individual bonds. And on the outside, both above and below, that's where the pi bond is. So pi bonds are usually a lot bigger than the sigma bonds. They're usually quicker to react because they're easier to get to if something's going to react with them. And that's also why in a double bond, it counts as just one big cloud. It's not a separate cloud because it's right on top of the other ones, which is just pretty crazy. So these molecules are flat, all right? It's just wild, but they have a whole different geometry. Like tetrahedral, you've got all kinds of angle possibilities and stuff. But boy, not when you have an sp2 trigonal planar system with a pi bond, then they're very flat, they're very two-dimensional. Pretty cool. You can have triple bonds. Acetylene is C2H2, also known as ethyne. And in ethyne, you have not just one, but two pi bonds. And if you look there on the right side, the top little small picture, that represents one set of bread. It's like above and below the sigmas. But the lower one represents the second pair of bread, and that's like left and right of the molecule. So when you have acetylene, you have these double slices of bread plus the stuff in the middle to make a triple bond. And triple bonds, again, are just one big cloud. It's like tons of bread. If you're not into bread, this isn't your kind of sandwich. But anyway, there's a lot of energy there because all those electrons are floating around. They're pretty easy to get to. So a triple bond is one sigma and two bonds. So again, if you see a molecule like acetylene with a triple bond, you have to realize that there's one sigma, maybe the middle bond right there could be the sigma, and there's two pi's. There's one above and one below. So a triple bond is two pi bonds and one sigma bond, which is pretty cool. This is a question you might see. It says how many total sigma and pi bonds are in acetylene, C2H2, and the Lewis structure is listed up there on the top. All right, so first of all, every time you have a single bond, that's a sigma bond. So there's one sigma right there, and there's one sigma between that CH right there. So that's two sigmas. And then in the middle there, you have that CC triple bond. You have one sigma and two pi bonds. So triple means one sigma and two pi. So if you count up all the sigmas, and you have to include the CH bonds, there are 3 sigma bonds and 2 pi bonds for 5 bonds total. That's going to be answer D, all right? So if you see a question like this, just don't forget the CH bonds. A lot of times people forget those, but they do count. They also have sigma bonds and stuff like that. Exciting times.
The carbon-carbon double bond prevents the ends of the 2-butene molecule from rotating freely relative to each other. As one end rotates, the energy of the molecule increases greatly because the carbon-carbon pi bond must be effectively broken. That is, there is a large energy barrier to rotation around the carbon-carbon double bond. Butane can rotate easily about its carbon-carbon single bond because the atoms of its methyl groups repel each other rather weakly. Rotation about this bond is accompanied by a small energy barrier and occurs readily at room temperature. The two sides of the molecule are therefore constantly spinning with respect to each other.
This double bond versus sigma bond becomes really important in organic chemistry. And a carbon-carbon double bond in organic chemistry, the names often have E and E. So if you see trans-2-butene or trans-but-2-ene, which is a newer way of talking about it, the E and E means a double bond. But sometimes, a lot of times, you'll also see compounds that have an A and E ending. Those are all single bonds between carbon atoms. So what we have here is a carbon carbon double bond in the middle part, upper middle part, and we have all carbon-carbon single bonds in the lower graph. And when you look at these two graphs, look at the difference between the top energy and the bottom energy for both of these. So for the double bond, it's 230 minus about 30, which is about 200 kilojoules per mole, top to bottom. But if you look in the single bond, it's roughly 80 and roughly 20. That would be a difference of about 60 kilojoules per mole. So those graphs are just basically telling us here that it has a lot more energy to rotate a double bond, which is what the top part is, going from the bottom to the top, a lot more energy to rotate a double bond than it does a single bond, which is what the bottom one is saying. And so in normal room temperature kind of things, the single bonds will rotate like crazy. They rotate kind of like this, like a propeller. They're just going round and round and round and round and round. They'll do that basically all the way down to 0 Kelvin, where all movement stops. On the other hand, boy, oh boy, if you have a double bond, those things don't move, all right? You can make them break and move, but it's very, very difficult, and it doesn't usually happen. So the E and E double bonds are much more difficult to break and make them rotate. And the single bonds, though, are easy to have that happen. We'll talk more about this at the end of Chem 223, but it's something to think about, how this extra pi bond just makes it more difficult sometimes to make one chemical turn into the other.